All right, so let's go over the practice test you took. This was the test I actually gave last year to the students. So your test tomorrow will be pretty similar to this, probably easier actually tomorrow. So here is our chance to go over it. Hopefully you actually did it. As of when I recorded this, only one person had, so I'm not terribly optimistic about that. But regardless, here are the answers, and please actually listen to the video and hear the explanation for the answers. Knowing the answers to the question will not help you. You need to understand the answers to the questions. All right, so here we go. Maximum insolation occurs in the northern mid-latitudes on or about June 21st, as you can see highlighted. That's when the sun is highest in the sky for us. It's up for the longest. And between the highest in the sky and the greatest angle and all that, that is why we get the most sunlight. Insolation, remember, is sunlight. Number 2, compared to the wavelength of radiation emitted, which means given off by the sun, the wavelength of radiation given off by the Earth is longer. So we get all sorts of wavelengths from the sun, but more light than anything else. And that light comes in, it hits the Earth's surface, and then the Earth gives back off heat. We don't give off light, we're not that hot. But we give off infrared or heat energy, which has a longer wavelength. Anytime a form of energy is absorbed and then re-radiated, it's always going to be longer when it's given back off. If you've ever seen the cool blacklight posters where you turn the light off, you turn on the black light, and the poster glows fluorescent, that is a situation kind of similar. It's absorbing ultraviolet and it's giving off visible and just seems very bright as a result. Same idea. Number 3, the coldest climates on Earth are found at the polar regions because the polar regions, they can have a lot of daylight. I mean, you could have 24 hours of daylight, potentially, at the poles. But because the sunlight's always coming in at a low angle, that means it's spread out over a big area, and it's not very intense. So that low angle is what causes it to be so cold, even during periods where the sun's up for months at a time. All right, the relationship between intensity of insolation and surface temperature is direct. That makes sense. The more intense the light coming in, the warmer it gets. When one variable goes up, so does the other. Totally logical. I doubt many of you would have missed that. Number 5. This one might have got you. For the latitudes of the continental United States, from March 21st until September 23rd, the angle of insolation at solar noon will do what? All right. Well, from March 21st until June 21st in the springtime, the sun gets higher and higher and higher in the sky every day. After June 21st, it starts to get lower in the sky every day, and we lose daylight until the winter begins, but in this range until we hit September 23rd. So that's why the answer is 2. It increases at first from March to June, and then it decreases from June to September. Number 6, most of the energy radiated from the Earth's surface is in the form of infrared. Again, we receive visible light from the sun, and we give off infrared slightly longer. Number 7, the least yearly difference in duration of insolation would be experienced at the equator, where you always have 12 hours of daylight. Here where we are in New York, we get 15 and a half hours of daylight sometimes, and down to 8.5 or 9. On the other end, so we have a pretty big range, like 7 hours. North Pole has a 24-hour range, so the equator has the least. Pretty straightforward. Number 8, this one probably tripped you up. Which of the graphs below correctly shows the relationship between the duration of insolation and the latitude for June 21st? Well, on June 21st, that's the summer solstice. And on the summer solstice, the equator, like always, has 12 hours, so they all except the last one start at 12. So the last one's out automatically because it has the equator at 24 hours of daylight. So we can rule that out. C shows everybody having 12 hours of daylight, which does happen on equinoxes, but June 21st is not an equinox, so C is out. B shows that as you go towards the North Pole, you get less and less light on June 21st, which is the opposite of correct because we get more light towards the poles. So the answer is going to be A. As you go northward, you have more and more duration of insolation, a longer amount of daylight, until you get to the Arctic Circle, where it's 24 hours, and it stays that way all the way to the pole. That's why the graph flattens out on top, is because it's already maxed out. Number 9, aerosols are little dust particles in the air, little solid particles in the air. Could be smoke, could be dust, could be pollen, what have you. As the concentration of aerosols in the Earth's atmosphere increases, the mean surface air temperature in the area beneath them will decrease. It blocks light from coming in. So if you block light from coming in, that is going to make you colder. If there were a bunch of volcanic eruptions around the planet and spewed tons of ash into the atmosphere, it would make the Earth colder because it would block light from coming in. All right, number 10, a greenhouse. So remember, the greenhouse effect here on Earth is the fact that we stay warmer than we would otherwise because we trap in some of the heat near the surface. It's called the greenhouse effect because it works similar to how a greenhouse works. So a greenhouse stays warm on a sunny winter day because the greenhouse lets in light, which is medium wavelength, and it traps longer wavelength infrared in, and infrared is just a fancy way of saying heat. Number 11, the diagram below shows the Earth at a specific position. Shaded area represents nighttime. What latitude receives the greatest intensity of insolation when we're in this diagram, or when we're in this position? Well, intensity is greatest when the angle is greatest. If you were at the North Pole, standing upright with your head pointing towards the top of the page here, the sunlight would be coming in, but it would be hitting you in the toes. Not a high angle, it's right on your horizon. At the equator, if you were standing on the equator, your head would be pointing off toward the sun, and the direct sunlight would be beating down on the top of it, perpendicular to the surface. So the equator on this day would have the most, that's why it's 0. Number 12, the addition to dust to the atmosphere will increase the amount of energy reflected by the atmosphere. It'll let less light in, it'll reflect it back out to space. It's like a giant cloud, kind of. So that's why that's 1. 13, we have 2 flashlights. They're identical in every way. Shine them on the globe. We place thermometers in the path of them, and we measure the temperature for 30 minutes. So students most likely observe that the temperature of A increased at, well, A is where it's shining straight in. You see the light's not very spread out compared to B, where it's spread out over a bigger area. So this is going to get hotter faster than B. So the temperature of A increased at a not slower rate, a greater rate, faster rate than B, because A received rays that were closer to or more perpendicular. All right. 14. The temperature of the atmosphere may increase as carbon dioxide content of the atmosphere increases. Which statement explains this? Carbon dioxide, water vapor, and methane are probably the top 3 gases in the atmosphere that trap heat. They let in light just fine, but when heat tries to get back out, they don't let it all get back out. So by increasing the amount of any of those, you're going to increase the amount of heat, infrared, that will be absorbed by the atmosphere, and it'll keep the surface of the Earth warmer as a result. So we've got our path around the sun, our normal orbit, North Pole always pointing at Polaris as we go around. Which position does New York State receive the maximum insolation for the year? That happens on the first day of summer, June 21st, which is position A, northern hemisphere leaning toward the sun 23.5 degrees. Between which positions would New York State experience minimum temperatures? Minimum temperatures happen about 6 weeks after the winter solstice, which puts us in January late January, early February. So the winter solstice is here. So January, February is going to be on the way to March. So it's going to be in between C and D, kind of close to C, but in between them. So that's why that's 3. 17, between which positions is the angle of insolation, the angle of sunlight at noon in New York, greater than average and increasing. No, wait, greater than average, but decreasing each day. So decreasing. That happens in the summertime. In the summer, the sun is above average. We're coming from our highest point on June 21st, and it's decreasing for the rest of the year. So it's above average and decreasing. So that's summertime would be between A, June 21st, and B, September 23rd. 18, gradual increase in, again, carbon dioxide. I'm going to beat this one into you. Carbon dioxide is the main greenhouse gas we worry about because its numbers are going up fast, and it's totally controllable on our part. So carbon dioxide warms us up because it absorbs heat, it absorbs infrared. Ozone is important to life on Earth because ozone is the one that stops ultraviolet rays from getting through the atmosphere. Ultraviolet gives you sunburns. It can also increase your chance of skin cancer. It can cause cataracts in the eyes. And that's just for us. Simpler organisms like bacteria, it can just kill them. One of the ways to sanitize from the COVID virus is ultraviolet light. So they put goggles, personal protective equipment, and UV light cabinets. Things that have soft eggs like frogs, it could kill those or damage them. So ozone is really important because it stops the harmful ultraviolet from getting to the surface of the Earth for the most part. That's right. Yes. The most logical conclusion concerning the relationship between insolation and ground radiation is that as insolation increases, our ground radiation mostly increases. So insolation increases, ground radiation increases. According to the graph, the time during which energy gained by the soil is greater than the energy lost by the soil is from wind to wind. So energy gained is insolation. So we gain energy here more than we lose energy from the ground. So we're looking for from here where they cross at 5 or 6 to here where they cross, which is really close to 4. So 6 a.m. to 4 p.m. That's why we choose that. That's when we had a surplus of energy. 22, the most logical conclusion concerning the relationship between the altitude of the sun throughout the day and the amount of insolation is that as sun's altitude increases, insolation increases. That makes sense. Sun comes up here, and the sun gets higher until solar noon, so the insolation goes up until solar noon. At which times are insolation and ground radiation equal, same as the answer to number 21, 6 a.m. when they cross and 4 p.m. when they cross. That's when we have radiative balance. That's the term we want to remember. So we have this graph showing surface temperature, insolation, and ground radiation for a year in New York State. Same diagram we had in the note packet. During which of the following months is the temperature the lowest? We said we're coldest in late January, early February. The scale's kind of funky. Oops, get out of there. Stop it. But we have December 21st. I guess it'd be January 21st. So, yeah, just at the end of January, beginning of February kind of thing. Weird scale. On the graph, either a maximum or a minimum occurred when the two lines crossed each other. Minimum temperature, when the deficit stops and the surplus starts, when insolation and ground radiation are equal. And maximum temperature, same deal, when we switch from surplus to deficit. So we have radiative balance. 26, compared to the time of minimum air temperature, the time of minimum energy absorbed from the sun. Well, minimum temperature is there, labeled minimum temperature. Minimum energy from the sun is minimum insolation, that's December 21st. So there's a lag there. There's that 6 weeks of lag. Now my scaling got a little weird because we went from Word to Doc, but December, January, February. So in December it was the least, in February it's the coldest, so 3 months earlier. The line on the graph that represents the mean surface air temperature is most similar to a line that we plotted to represent the temperature pattern that would occur for a day, meaning, if we look at this graph, we have a minimum temperature, we have a maximum temperature. They happen when we have radiative balance. Now, the daily chart would not look exactly the same by any means, because at night we get no insolation, so the line has to be different. But overall, it makes sense that would be the one for a day. If it were a month, you'd have 30 up and downs, 30 highs and lows for each day. But for an hour, you probably wouldn't have a minimum, maximum, that much of a cycle. And for a week, you'd have your 7-day cycle. So it just doesn't work. All right, so we got a light bulb shining energy on the water and on the soil. And the soil got hot. The water got hot, but not as much. We turned off the lamp and then it went back down again. In a normal year, we would have done this lab, but this is not a normal year. So we're just reading the graph mainly. What were the temperature readings when the lamp was turned off? Well, you just had to read the graph. So, I mean, there's no rocket science to that. Water was 28, the soil was 45. This process transferred, by which process was most of the energy transferred from the lamp to the water? Well, they weren't touching, that would be conduction. Reflection is what can happen, but it doesn't transfer energy. Convection, another transfer. But you have mixing of liquids, and there's no mixing here. Radiation, energy traveling from the light bulb to the soil or to the water through more or less emptiness. That's what we had. So that's why it was radiation. Rate of temperature change. So the formula for rate of change is right on the front of your reference tables. Change in field value over time in this case. And so we have our change in temperature over our number of minutes. You just had to make sure you do it for the soil, which started off at 20, and after 10 minutes was up to 45. So it went up 25 degrees in 10 minutes, which is 2.5 degrees Celsius per minute. And compared to the water, the soil became warmer during the heating period because the soil has a lower specific heat. It takes less energy to heat up the soil relative to the water, so it gets hot faster. This is a graph of solar radiation that gets to the Earth's atmosphere. Not what actually gets to the ground, but what strikes the outer atmosphere. And we can see the measurements recorded for a whole year there. All right. So you had to read the graph. There's a lot of little lines, so that could have messed with your eyes, I suppose. But you just had to read the graph. Should have gotten 1.92 calories per square centimeter per minute. Maximum amount of solar radiation reached the collector during January because, well, this is a little tricky. Remember, this is from the last topic, or actually a topic and a half ago. Earth was closest to the sun. That's why we'd have the most energy in January, because this is outside of the atmosphere, ignoring the tilt. The solar radiation reaching the collector would be mainly visible light, because that's what the sun gives off more than anything else. And 35, on November 1st, the amount of insolation reaching the collector was 1.970 calories per square centimeter per minute. Less than this amount would get to the surface because, as we talked about, some of the energy is scattered, some of the energy is reflected, some of the energy is absorbed in the atmosphere, and so it doesn't all get to the surface. So slightly less than half of it actually gets there. So that's why 35 would be number one. 36, you have a solar collector placed outside. Which one would have the most intense radiation? Well, in order to be most intense, you want the light to strike the surface at a 90-degree angle, straight in, perpendicular to it. So C has rays of light shining straight in. So that's why that's C. Main purpose of the insulation behind the plate. So you see up here in the picture, you've got this absorbing dark plate and then insulation behind it. Well, what's the whole purpose of insulation usually? To stop energy flow in a certain direction. So it will decrease the amount of energy lost through the back of the collector. You want that heat to go in, cold air goes in from the house into the bottom of the collector. It warms up, it rises up through the collector, gets warmer and warmer and warmer. Then it goes out into your house. Cold air is denser, it sinks, it gets sucked in. This would work without any fans or any fancy electronics, it just happens. So, kind of a neat concept. What paint should be used on the absorber plate to get the most energy possible? Dark paint, black paint, because it absorbs all wavelengths of light. So that's why black. 39, the main function of the glass cover. Well, glass, like in a greenhouse, like in windows, allows light to come in, but it doesn't let heat back out again very well. That's why cars get so hot in the summertime. Light gets through the window just fine, but when it tries to go back out of the car as heat, the glass stops it. And so it builds up to very, very warm temperatures in no time at all. Same deal here. You keep the glass plate on top and the heat gets trapped inside. Last one. Why does the air usually enter the collector at the lower air inlet and leave at the upper? That has to do with density differences. Cold is dense, warm is less dense. Warm air rises because it's less dense. So the air inside the collector is less dense than the air in the lower inlet. Number 2. Thank you. End of story. So your test is going to look pretty similar to that. So if you didn't get it all the first time, rewatch the video. If you didn't do the sheet the first time, you should have. So that's what we have. Thanks for watching.